In this video, we consider inverse trigonometric functions, both composite functions and algebraic forms. It corresponds to material found in section 7.2 of the textbook. Up until now, the composite functions we considered were inverse functions of each other. For example, we looked at the inverse cosine of the cosine of x. Now we're going to evaluate other combinations of trig functions. Let's begin with the sine of the inverse tangent of 1/2. Let's define theta to be the inverse tangent of 1/2 and solve for theta first. We rewrite the expression as the tangent of theta equals 1/2. Now, because we are really working with the inverse tangent, theta is restricted to being between minus pi over 2 and pi over 2. Ignoring that angle restriction for the moment, we know that the tangent of theta is 1/2, which means that, generally speaking, the angle theta lies in either quadrant 1 or quadrant 3. So we have two sets of constraints on theta. The only angles that meet both criteria are those found in quadrant 1, the angles between 0 and pi over 2. The figure on the right shows a possible value of theta. The terminal side of theta crosses a circle of radius r. The tangent of theta is defined to be y over x, and since it's equal to 1/2, we can say that y is equal to 1 and x is equal to 2. And the point P at 2, 1 lies on the terminal side of the position angle theta, r units away from the origin. We use the Pythagorean theorem to obtain r, and we find that r is equal to the square root of 5. We're interested in finding r because that will help us solve the overall problem. Remember that we're interested in finding the sine of theta, where theta is the angle whose tangent is 1/2. The sine of theta is defined to be y over r, and that's 1 over the square root of 5. When we rationalize this function, we get the square root of 5 over 5. Now let's look at another example. Here we're trying to find the cosine of the inverse sine of minus 1/3. We define theta to be the inverse sine of minus 1/3, which we rewrite as the sine of theta equals minus 1/3. And because the expression is based on the inverse sine, the values of theta are restricted to being between minus pi over 2 and pi over 2. Now, the sine of an angle is defined to be y over r, and because r is never negative, if a sine is negative, this means that y has to be negative. And if y is negative, that means theta must be a third or fourth quadrant angle. The constraint shown in blue, that theta must be between minus pi over 2 and pi over 2, places theta in quadrant 1 or 4. Combined with the constraint shown in purple that we've already talked about, this means that theta must be a fourth quadrant angle. That is, it's between minus pi over 2 and 0 radians. Theta is shown in the figure on the right. Sine theta is defined to be y over r, and for this particular theta, it equals minus 1/3. So we can say that y is equal to minus 1 and r is equal to 3, recalling that r cannot be negative. So we say that there's a point P at x, minus 1. That's 3 units away from the origin, and it's on the terminal side of theta. We don't know yet what x is, but we can find x by using the Pythagorean theorem. And we see that it is the square root of 8. So when we solve this, we take the square root of 8, we find that there are two solutions, 2 times the square root of 2 and minus 2 times the square root of 2. Since theta is in quadrant 4, x must be positive, so that means that it has to be 2 times the square root of 2. The cosine of theta is x over r, which is 2 times the square root of 2 over 3. And that's our solution. So far, we worked with the inverse sine inverse cosine and inverse tangent, but the other trigonometric functions can also have inverse functions, with restrictions on their domains and ranges. For example, the inverse secant function is domain restricted in that the absolute value of x must be greater than or equal to 1. And the range is restricted as well. The inverse secant must be between 0 and pi, and it cannot equal pi over 2. The inverse cosecant function is similarly restricted. Not exactly the same, but similar. And the inverse cotangent function is also restricted. There are situations in which we can transform an expression involving trigonometric functions into an algebraic expression. Here is an example. We have the sine of the inverse tangent of u. We can let theta equal the inverse tangent of u. And we can write this as the tangent of theta is equal to u. Because we're really working with the inverse tangent function, the value of theta is restricted. It must be between minus pi over 2 and pi over 2. U, however, can be any real number. Based on the restrictions on theta, we can see that it must be in the first or fourth quadrant. In those quadrants, all values of x are positive, so the secant of theta is also positive. We know this because the secant of theta is defined to be r over x, and r cannot be negative. So because r can't be negative, we know that the secant of theta must be greater than 0. Now let's go back to the original expression. Since the inverse tangent of u is equal to theta, we can say that the expression equals the sine of theta. Now we multiply the sine of theta by cosine theta over cosine theta, which is the same as multiplying it by 1. We regroup the cosine theta terms and substitute tangent of theta for sine of theta over cosine theta. This gives us tangent of theta times cosine of theta. That's equal to the tangent of theta over the secant of theta. Earlier we studied some trig identities. One of them was the secant squared of theta is equal to 1 plus the tangent squared of theta. We use this identity to rewrite the ratio tangent of theta over secant of theta, and we obtain the expression shown in red. Then we remember that the tangent of theta equals u, so we substitute u into the equation. The result is an algebraic expression that does not contain any trigonometric functions.